minutos. Les damos la bienvenida y nos da gusto que estén aquí en la conferencia del doctor Richard Weaver de la Universidad de Illinois. El doctor Richard Weaver es físico, teórico especializado originalmente en cosas de astrofísica y en cosas de física teórica, pero tuvo su entrenamiento en mecánica con el auspicio del profesor Pau, uno de los expertos y íconos de la mecánica de sólidos, estudiando mecánica de placas. Mucho de su trabajo es sobre vibraciones en placas y su trabajo pionero es los cálculos de las curvas de dispersión de placas, todas las ondas de Lamb. El doctor Weaver ha desarrollado una importante experiencia en física estadística, generalizando las ideas de acústica, lo que se llama acústica, room acoustics, y generalizó a la elastodinámica muchos de los desarrollos de esta disciplina. Él, conjuntamente con otros y en particular con Michel Campillo, es de los impulsores y de los iniciadores de la llamada sísmica pasiva, de manera que sus desarrollos pues son los que marcan el inicio en el siglo XXI. Sus trabajos de 2001 muestran experimentalmente con ultrasonido esos datos. Luego, poco después, Michel Campillo logró hacerlo en la Tierra y mostrar la evidencia de ese efecto que hoy en día mueve a muchísimas ramas de la sismología y la industria en la parte de exploración y también la caracterización de sitios con algunas de las derivaciones que tenemos el gusto de haber hecho con el doctor Weaver. Ahora nos va a platicar sobre una de las derivaciones de esta técnica, cómo lograr mejorar las correlaciones mediante para la obtención de la función de Green mediante ponderación apropiada de los eventos. El doctor Weaver además es un teórico fino y podría darles satisfacción a sus preguntas, y estos días hemos tenido el privilegio de contar con él. Estará por aquí el día de mañana, se va pasado mañana, de manera que les agradezco su presencia, y al doctor Weaver le démosle la bienvenida con un aplauso. Buenos días. Welcome.
Thank you, Paco. Do I need this microphone? Yes? No?
Because of the streaming.
Oh, because of the streaming, okay. And it's coming through fine? Okay, it comes through fine. All right. Thank you, Paco, for bringing me here and giving me a chance to talk to you and your colleagues about all these things. I am very grateful for your kind hospitality, and you are feeding me much too well. So, thank you. My apologies for speaking in English, but believe me, you do not want to hear me speak Spanish. I've been working for some time in this business of Green's function retrieval, and we have a bunch of theorems that say that you should be able to, by correlating random noise, be able to construct the Green's function. That is the signal you would have if you had a simple source and a simple point receiver and such. And this technique has been around for a while now, and it's had a number of notable successes, but in our naivete as theorists once upon a time, it works much better in our imagination than it does in practice. There are a number of difficulties with it, and a number of people have experimented or tried out techniques for trying to improve the process, and with varying degrees of success for different enterprises and different purposes. And this is my contribution to the business, and I think I have a technique which works very well in theory again, and I would like to see how well it works in practice, and this is one of the reasons that I'm excited to talk to you, because maybe with your access to all these huge data sets, you'll be able to apply these techniques. I think they're not very complicated, and I think that that's a reason to suspect that people will find them possible to apply and will, I hope, find them useful. So that is the beginning. And I'll start with the background. There are some theorems that when a noise field, imagine an acoustic field coming from all directions, consisting of randomly propagating and scattering waves and so on, when it is perfectly diffuse. And by that, I'm not going to go into the definition of that because it can get a bit subtle, but we'll just say in practice, real fields rarely are perfectly diffused. But if we satisfy this condition on the statistics of the noise field, then its correlations will retrieve the system Green's functions, or as we have in our equation here, that the correlations well, we'll use this one. The correlations here are just defined as some kind of average of the field, and I've used a scalar, I'll be talking about it in the context of scalar waves, but you can imagine this is a vector field. At a sensor position, x sub I, at time t, is not entirely independent of the field at another sensor position at a later time. And if you perform this average, and in practice this average is a time average usually, but the theoretician usually imagines an ensemble average, that just gives you the definition of this correlation function between sensor I and sensor J at some lapse time tau. And the theorem states, not to make it too complicated, that essentially this correlation function is the sum of the regular Green's function and an anti-causal one, because of course this in principle can be symmetric, so you have results at negative taus as well as positive. However, these are very easy to separate because this only has support at positive tau, and therefore this only has support at negative tau. And so the theorem states that if the noise field is fully diffuse, and I haven't defined that completely, but I'll give you some insight into that in a little bit, then in fact you basically get that the correlations are the Green's functions. There are a few other subtleties that are worth mentioning in passing, though they're hardly critical for us right now, and that is some people have noticed that you really should put in a time derivative here. And then the other thing that's worth pointing out is that the noise field usually consists of a fairly band-limited, only certain frequencies. And of course the Green's function is something that includes all frequencies. So actually what the correlation is a band-limited version of the actual Green's function. And let's remind ourselves that the Green's function is the response you would have at one position if you had an impulse at another position. And as such, it's sort of the ideal acoustic experiment. You tap it here and you see what comes out there. And that's essentially all the information that you can hope to get by doing wave propagation in a medium, sort of digging holes and seeing what the rock is and such. So that is what we would hope to be able to recover. And from that, we hope to be able to understand our medium. So this permits us to assess system properties without having to put in a source. I come from ultrasonics. I've got a block of a solid here. I put a tap here, and I measure the response over there, and I can tell something about the medium. A source for me in ultrasonics is a very simple thing. However, in seismology and in ocean acoustics and so on, a controlled source can be a very complicated thing. At long period seismology, you need an earthquake, which of course is not controlled, or a nuclear explosion, which is far from convenient. So what this allows us to do is to probe the wave-bearing properties of a medium with our choice of where the sources and the receivers are, just by putting receivers. We do not have to generate sources. And this observation has led to a lot of remarkable work correlating ambient seismic noise. As I say, that seems to be the chief application because sources are inconvenient, controlled sources are inconvenient in seismology. The advantage for ambient seismic noise, which is usually stuff that's all around it, it tends to come, I think, from the ocean, at least at long period, and then at shorter periods you tend to find ambient seismic noise due to traffic and human activities and such. The advantage of ambient seismic noise is there's a whole lot of it. It's basically continuous in time for months on end. The disadvantage, it's not fully diffuse. It's not equipartitioned, as we like to say in the business, or more specifically, the intensities are not coming uniformly from all directions. That's one of the chief requirements of a fully diffuse field, is that the noise field should be of equal intensity from all directions. So the ambient seismic noise field is not fully diffuse, and nevertheless it works. And here's one of the first examples of that. This is a correlation trace between two stations in Southern California. And this is the result of 1 month of correlating the seismic noise. Here are 4 different traces from 4 separate 1 month correlations. And essentially the thing that you get out is independent of when you take the correlation. And this is the signal suitably processed from an earthquake which happened near one of the stations and was received on the other. And so what you see here is from the correlation, you get the same information you would get if you had a source next to one of the stations. And of course, we don't always have an earthquake where we would want it for this purpose, so this gives us the wave field, the signal that we would have if we had had an earthquake at the various other stations. And so what you pick out from this very quickly is the arrival time. And the arrival time is independent of whether you have an earthquake, you're doing a correlation, or whether you did a correlation at a different time. I should say, by the way, that we have plenty of time here, and I understand that I sometimes speak very quickly. Please, if you want to interrupt and seek clarification, I would like that, because then I would know how well these ideas are coming across. So please, maybe I should stop and ask, does anybody have a question right now? Too shy.
I want to know, what about the amplitude of that? When you compare the amplitude of the earthquake and the cross correlation, they are the same, or?
Very, very good question, and that is when we recover these correlations, what's happening to the amplitude? According to the theorist, the amplitude of this depends upon the energy density in the diffuse field. And of course, you can't even compare it with the amplitude of the earthquake because they have different units. However, you might be able to compare relative amplitudes between different stations, and then it's just a matter of being very careful about your signal processing. Mostly, though, what we look at is we just want to make sure that the amplitude we see here is well above the noise background so that we can trust that. Does that answer your question? Yes?
What about the time lapse?
The
Time lapse?
The time lapse?
Time lapse, I mean, t plus tau, or tau plus t,
Yes.
how big, how short the lapse?
In this particular application, this time lapse was or something of that, I'm not sure. Maybe it was a couple of 100 seconds and so on. If I back up, here, yes, in this formula, T is a time period that you're usually averaging over, and that may go up from months. Tau is usually the lapse time, and that's usually minutes. So, but you could also fix T and do an ensemble average. That's just not practical. So when you construct these things, you're actually usually integrating over little t over a period of hours to months. And where tau is a fixed time when you do this averaging, which has a value on a scale of minutes.
But I would guess that the correlation would give you different results. Do you have it without?
Yes, so this plot that I have here
Pardon.
is a plot versus tau. They've done it versus group velocity, so that's distance over tau or something like that.
Okay.
It's a little complicated because they were most interested in pulling out the group velocities.
Right.
But essentially, that is lapse time.
Okay, all right.
Okay.
Thank you.
So from that work, it can lead to rather striking maps of seismic velocities. From those preceding pictures, what they managed to pick out is the travel time or the group velocity between every pair of stations for which you can get reasonable signal here. And if you have the group velocity between every pair of stations, you can see them, there's 60 or so of them in here. Those are the little dots. You have travel times between every pair, and tomographically you can reconstruct a map of how the velocity varies from place to place. And this map, I think, is just lovely. Even with my understanding of seismology, I can see that there's something interesting going on here. And you can see the sedimentary basin here in the San Joaquin Valley, and you can see the Sierra Mountains and so on, where the wave speed is high. So it works really nicely in this way. You can invert these arrival times by using tomography, and you can construct these maps of wave speed versus position, and you can do it at different frequencies, and you can get a different map at different frequencies, which, if it's a surface wave, corresponds to different properties at different depths. So you get information as a function of depth as well as a function of x and y. And by the way, the resolution here is comparable to the spacing between the stations, so you have as much resolution as you have stations. So that works. People look at that map and they say, yes, this makes sense. But there are a number of people at the time quite rightfully said that if you look at the theorem, it shouldn't work unless the field is fully diffuse. And we know that the ambient seismic noise that was used for a map like this was mostly, but perhaps not entirely, energy that came from the North Pacific due to storms in the North Pacific. We don't really fully understand where this stuff is coming from, but we do know that it's not an equal intensity from all directions, and that's one of the requirements of a fully diffuse field. And in practice, seismic noise fields are very rarely fully diffuse. Some directions have more intensity than others, and most noise fields have, and this is a term that I invented, I just like it, Michel echoed it back from me with a certain sense of humor. He liked it too, I guess. I just call it P of theta. You could alternatively say the angular distribution of incoming intensity, but that's sort of a mouthful. So if we just use this word ponderosity, which means weighting, as a function of angle to indicate how isotropic the diffuse incident wave field is. We can do a further theorem, that came out a couple of years later, that if P is smooth, that is, if the energy intensity coming in varies slowly as a function of direction, so you might have more from the east than the north, but the transition is fairly smooth. And if the medium has no scatterers. So as we say in the business, propagation is ballistic, it's just rays, and there's no scattering. If that's the case, there's an alternative theorem that says the correlation function is still the Green's function, but we have these extra factors in front, which is essentially, this is the intensity at position I, at sensor number I, going towards station number J. So the correlation that you get between I and J depends upon what the intensity was at I going towards J. And that's different from the intensity at J going towards I, which shows up in this other term. Nevertheless, if this is the case, you still look at it as a function of tau, you can see this wave packet arriving at the arrival time of at the appropriate arrival time, and you can from this still pick out travel times. The effect of this non-constant P is that the amplitudes have been changed. They depend upon the direction of interest. And this isn't an exact identity. There's some small corrections asymptotic in the smoothness of P, which, roughly speaking, you can say they're small, like the square of the separation distance between the sensors in units of the wavelength over 2 pi. Sounds like a big mouthful to say. In practice, this is much less than a 1% effect, unless your stations happen to be very close, and if P is not very smooth. So we have a way to rescue the theorem. It works anyway, and that explains why this stuff comes out so well. The noise field from here was mostly from the North Pacific, but it varied fairly smoothly in direction, and so they were still able to get nice arrival times. The amplitudes here were affected by the precise direction that the orientation between the stations, but if you're interested in arrival time, you basically don't care about that, as long as you have decent signal to noise. So this is our updated theorem, which works, and I should emphasize the critical condition for this is that there are no scatterers, and I'm going to be getting into that in a short period. I have a little bit of a numerical simulation in support of that theoretical assertion that it's possible to handle ponderosities which are not constant, that are not isotropic. This is just a restatement of the equation in the preceding slide, and this is a numerical simulation on an array that translates in seismic practice to about an 800 by 800 kilometer array. I have 6 seismic stations here. It's a scalar wave equation that I'm solving, and I have a distribution of sources given by the black line here, which is fairly weak here and fairly intense over there. So it satisfies the conditions of the preceding theorem. There are no scatterers here, and we have a smooth variation of intensity as a function of angle. And in the scaled units, I have 4 months of time varying and direction varying band limited ambient noise at a period of around 10 seconds and so on. And what we can find with this is the correlations. I had 6 different stations here arranged from east to west and so on, just labeled 1 through 6. And I construct the correlations on this particular plot between station number 6 and the other 5. And what we can see here, first of all, we'll see that you can see that you see something happening at negative tau also, and here stuff at positive tau. These particular fellows here are due to correlations from point 6 towards numbers 5, 4, 3, 2, and 1. So this is the correlation from 6 to 5. This is the correlation from 5 to 6. Or alternatively, think of it as just the negative time version. So these things depend upon the intensity at 6 going towards the left. These guys depend upon the intensity, well, this particular one is the intensity at number 5 going towards number 6. This one is the intensity of the ambient noise at 4 going towards number 6. It's possible when you look at plots like this to misunderstand them, but once we sort out the details, we can understand it. Here on the right, the things that correspond to propagation from 6 towards the left, we see a greater and greater distance. It took longer time to arrive. You also see a diminishing amplitude, and that's because the medium had some attenuation. And also, of course, there's geometric attenuation. And you get something that's fairly easy to interpret. And what's more, because we were careful about the amplitudes, we can interpret this decay as attenuation. And in fact, that does correctly recover the known attenuation I put into the numerical simulation. So this is due to an attenuation, e to the minus alpha times the distance, and some geometric attenuation also. And the reason it works so nicely is that this has an amplitude proportional to the intensity at 6 going to the left, this at the intensity at 6 going to the left towards number 4, and so on. Each one of these has an amplitude which depends upon the intensity at 6 going leftwards. These are rather subtly different. This is the intensity at number 5 going towards number 6. This one is the Green's function with an amplitude which depends upon the intensity at number 4 going to the right. So these things, if you compare the amplitudes, you're not comparing things that really should be directly compared. And what we see here, if you weren't careful, you would think that there was no attenuation. But in fact, we see a rather complicated mixture of the effects of the attenuation due to propagation and the fact that the intensity at 1, 2, 3, 4, and 5 moving towards the right is different. And that's because the ambient noise was suffering from attenuation also. This is partly an aside. It's not really terribly important for my main point today, but I did want to say that we can recover amplitudes and we can recover attenuations, but we have to be careful about that. And also, we should point out that this was for a case where the intensity coming in was not isotropic, but there were no scatterers, and so you get pretty clean functions here. You have to make some effort to interpret the amplitudes, but we have good signal to noise. It basically is working, with the slight caveat that you have to keep track of the effects of the P of theta, the effect on the amplitudes. But you still get Green's functions. You just have to be careful about the amplitudes.
How many sources are you using, Professor?
Lots. They were distributed over this volume. There were probably thousands.
I imagine.
Well, it's a little hard to say how many sources do we have when we have ocean acoustics. Is each? It's hard to say.
We have tried with some few and tried to fulfill the equations. And it's very important when you have a single wave that crosses from the source to one receiver or two receivers, coupled in that direction, as you mentioned, as a ray, so you can have some certain distributions that may work.
Yeah, if you have not very many sources, if they're distributed just right. Yeah. So, the method works if we have fully diffuse, which we don't in practice. It also works if the ponderosity is smooth, but if P is not smooth, and there are lots of ways it could be not smooth, or if they're, oh no, I guess I'm just working on the point source here. Let's go back to, this is a medium without scatterers, and instead of having a distribution, a smooth distribution of sources out here, let us just imagine a point source. So I don't really have a diffuse field at all. This might be something you would superpose on maybe you have a distribution of point sources or noisy sources out here, but one really loud one. What if right in the middle of your looking at the ambient noise there was an earthquake or something that went off at one point? If you have something like that, the effect on the correlation should be, we should need to understand its effect, and one of the chief effects that it has is things that I call spurious arrivals. Imagine a point source here. Here's two stations I and J separated by a distance D. This point source is noisy. And then we ask now, what is the similarity between the signal that arrives at point I and point J? They essentially are very different at most times, but at a time corresponding to the difference in travel times to the point source, we find the same thing going on here. So there's some little blip in the source here. It takes a certain amount of time to arrive there. It also takes a certain amount of time to arrive there. And those things will therefore be highly correlated at a time which is equal to the difference in the travel times. And so if you did the correlation from just a point source, you're going to get something that looks like this. Add an arrival time, which corresponds to the difference in the distances. This is where you should see an arrival at the travel time between I and J. In practice, what you're going to get this. You definitely do not get the Green's function. In fact, what's even worse, you get something which is non-causal. That thing does not belong in any Green's function at all because it's arriving before the first thing should possibly arrive. So that is one of the problems, and that's an example of what happens when you have a non-smooth ponderosity. It has been thought in the early days that multiple scattering would smooth P enough to do that. Go back to this picture here. If you had a point source here, but maybe lots of scatterers in there, maybe you could imagine that the rays that finally arrive at I and J end up coming from all directions in a nice smooth way. And this was sort of a hand-waving argument that suggested in a multiple scattering medium, it doesn't matter too much what the source distribution is because the many scatterers here will homogenize it. And it's not entirely, it doesn't entirely work. It's arguable that such scattering actually makes things worse. I can consider an example where P is smooth but non-uniform. So forget my point source, but maybe I have more intensity coming from the east than the north in some nice smooth way. But if there's a scatterer here, then in fact, again, the scatterer looks like a source. So again, it looks like an independent source, a point source, and you would get a non-causal phenomenon here. Because the sources out here would send their energy to a scatterer, which then sends energy off to J and I separately, and the signal at I and J are correlated on a time scale of the difference in travel times from the scatterer to the stations. A scatterer will look, according to this argument, just like a point source, and it leads to the same kind of non-causal, spurious arrivals that do not belong in the Green's function and can confuse the interpretation of the correlations. It's a little bit of a puzzle, again, very tangential, but it's worth mentioning that people have discussed why is it that the scatterer like this doesn't ruin the correlation in the case of the field being perfectly diffuse. And it turns out the signal that goes from the scatterer to these stations here is a sum of energy that came in from the sources, hit the scatterer like this. It also depends upon the sources way out here that hit the scatterer and then were shadowed. because it was knocked out of the thing. If you look at that in detail, they all cancel each other, and you end up getting the theorem that we already knew. If the field was fully diffuse, you don't get this non-causal thing. But if the intensity here and the intensity there are not the same, then in fact you don't get the cancellation, and you get these non-spurious and non-causal arrivals. You also generate stuff that doesn't belong at later times after the causal arrival. So that is all by way of background. Now I want to start talking about my techniques for maybe improving the correlation functions. This, in fact, is a simulation of a correlation in a multiple scattering medium with a smooth ponderosity but a non-constant ponderosity. And it's a multiple scattering medium. It's a numerical simulation, and you can see that it's a relatively horrible Green's function. There's lots of stuff happening here at times before there should be anything. There are at least two sources for getting bad correlations, bad empirical Green's functions. One, which we think we understand pretty well, is that there are problems just if you didn't average enough. We in practice only have records that go on for so long, months or even less, that if that is not enough time, if we haven't averaged enough, you can be left over with things that are just residual because you just haven't averaged enough. And I call those finite T noise, capital T being the amount of time you're going to average over. Typically an application that's months. And you would like it to be as much as you can, because that by averaging longer and longer, you'll smooth things out and depress the fluctuations. We think we understand that. But what seems to be far more important are these spurious features, often non-causal, like you see right here, due to either a strong point source noise, as I described earlier, or scatterers in a non-isotropic, non-fully diffuse noise field. And this, as I said, is a numerical simulation in such a case. This is two stations separated by, it looks like about 150 seconds at a fairly high frequency, I think about 10 seconds or so on. And we see in here, for starters, you can just look at this and know it's not a good empirical Green's function, because there's all this stuff happening at short times before there should be any arrival. I've also plotted on this thing a red line, which I hope you can make out. That is a priori estimate of the effect of finite T noise. When you look at something like this, you might think, oh, let's just average for more than whatever it was, 4 months or whatever. Maybe it would get better. But this is the level of the noise that you have because of having finite T. The error that we have in here, that high amplitude stuff here at early times, is not finite T noise. It will not go away if you average for more time. There's no point in making that effort. It's due to this other effect, these spurious features due to multiple scattering and non-smooth ponderosity. So that's an example of something which we don't like, but averaging a greater amount of averaging in time is not going to improve it. And what I would hope to do is find another way to treat it in order to improve that thing. So this is my goal. I want to improve such retrievals. If you have, as we do in seismology, incident energy which is not constant in direction, and if we have scatterers, we know from these arguments earlier that we're going to get features in there which do not belong in the Green's function. And the example I just gave you here, it's very, very, very bad. You see non-causal things in there that definitely don't belong. But in practice, if you're doing seismic correlations and you in January, say you've got a big storm in the North Atlantic, and maybe in March you've got a big storm in the Gulf of Mexico, and another time you've got a big storm in the Pacific, and so on. On the average, in some sense, you might imagine that it kind of averages out. However, that's not really true. Tends to be that perhaps nearby storms and so on tend to be louder and so on. You can't just average over a long amount of time and hope that the effective ponderosity is constant. But maybe with the right kind of signal processing, we can still do an average in time which makes our effective ponderosity more uniform. And that's the idea behind the approach that I'm going to be taking. Let me start with just a definition. This is the field at station number I as a function of time on day number D. And I arbitrarily, do we have a question? I'd be happy to answer a question. In fact, maybe I should stop and ask for questions again before going any further.
So your goal would be to, by processing, by right processing, avoid long periods of time, recording long periods of time?
What I want to do is recognize that my P is varying in time as well as an angle. So maybe by weighing it properly, I can make the total P uniform in angle. So on day D, I get this particular, or a window D, I get this signal on station number I, and within that day, and we may have hundreds if we have 4 months of data and so on, you can construct the array of correlations for these individual days or time windows and so on. So this is the correlation from a fairly small amount of time between the stations I and J. And again, T, the integration, is usually over some time of the order of a day or weeks, and tau is the lapse time is of the order of minutes. And here's my correlation again. This is what people usually do, is they take the day's correlation and you make a straight stack of this thing. You just add them all up, you do the average over the full 4 months. And that is what most people have in fact plotted, though there are some slight variations on it. But that's essentially the standard procedure for doing correlations. You take the correlation from each separate day and then you just add them together. And that's equivalent to doing a correlation over the entire 4 months. But it's equally valid to weight the sum relatively arbitrarily. And so I've just done the same thing with some set of weights lambda, which vary from day to day, which I have yet to choose. And you can show fairly straightforwardly that this stack you find here is the correlation that you would get if the actual ponderosity were this, where that's the ponderosity on that particular day, and this is the effective. What you'd like to do is choose those lambdas so that this thing is relatively constant in angle. Before getting into that, we just recognize this is just as valid for any choice of the weights lambda. In fact, all it's doing is just saying, let's pretend the data was exactly the same, only it was a little bit louder on one day and a little bit weaker on another. So it's perfectly valid, but the big question is, how do you choose the lambdas? How do you choose the lambdas so that you get the result here to be as nice as possible? And there are lots of, lots of different ways that you could choose them, but what I'm going to do is define a sort of a measure of how good or how bad the correlation that I construct this way is. For not terribly important reasons, I often start by just normalizing the correlation of any given day by the total energy on that array. This is done without any loss of generality because we could define our lambdas to change this. But it's a standard procedure that I have called flattening, which tends to make each day of your 4-month period contribute equal amounts of energy, so that you're not dominated by one day where the storm happened to be especially loud. Thank you. But that we can undo that in a bit if we like. And now I do this normalization, but then I construct this weighted stack with these lambdas, which I do not know yet. But I'm going to choose these lambdas. Ideally, what I'd like to do to choose the lambdas is such that the effective ponderosity is in fact uniform. But I don't know the ponderosities on each individual day, so I don't know how to do that. All I can do is look at this X and ask, do I like it or not? And I need some criteria for deciding if that X is something that I like. And I have some measures of the badness, I need a better word than badness of X. This is one such measure. This is an integral over time of X minus its time reversed version. So what this measures is how anti-symmetric the X is. If things were nice, if things were isotropic, then X should be exactly symmetric in time, and capital S, this measure of badness of antisymmetry would come out to be 0. So we'd like to make S 0. Another possibility is if you believe that there should be no correlation at short lapse times, because you know that the maximum speed can't be more than a certain amount, you could define this thing, which is the integral of x's energy over a time interval which comes up to the expected arrival time. So this is a measure of the A causality, which you'd like to set to be 0, and this is a measure of the antisymmetry, which also you'd like to set to 0. There's some freedom in this. You could define these time intervals in various different ways, but roughly speaking, these are the two approaches that we have. With those definitions of S and C, the badnesses, we can construct fairly straightforwardly what S is in terms of the lambdas. In fact, it's not hard to show at all that S and C are both quadratic in the lambdas. So in fact, and these are the definitions of these matrices. If you have 100 days, this is a 100 by 100 matrix, and lambda is a 100 component vector, and this particular construction here is a fairly standard quadratic form that gives you the badness that you would have for specified lambdas. What you'd like to do is minimize these things. Minimize the antisymmetry, minimize the non-causality, but if you do a straight minimization on it, you quickly find the way to get no non-causality is to have no weights at all, and you have no signal, so that's obviously not what we want. So you need to throw in some kind of constraint. When I first started this, I thought the most obvious possibility, just because when you do L2 norms and matrices and so on, the standard norm that you would have is something like this. And you could just constrain the minimization of S and M by making sure that the norm of lambda is equal to 1. You can sort of see right away that's not something that's expressible in terms of X, but you can certainly take that as a norm. What ends up being more useful is this is a measure of the total energy in the stack, because it's the sum of all the autocorrelations in the final stack, and you can show that this is written very easily in terms of the lambdas. And this is another measure of the energy in the entire stack and all the waveforms. And again, this is a quadratic form in the lambdas. So those are three candidate ways of constraining the minimization on S and C. So I've got those two measures of badness, symmetry and causality, and I have three choices of constraint that I just described that gives us 6 candidate schemes for finding an optimal set of weights. In addition, there are 2 more procedures for choosing the lambdas. The conventional straight stack where you didn't do any of this, and the flattened, the one where you normalized by the energy in each day. So it gives us what I call 8 different schemes for choosing the lambdas. The conventional stack is just to remove that normalization that I described earlier, and that's just to set the lambdas equal to the individual energies in each day. This is the flattened method. What it does is choose the weights such that each day has the same amount of energy. And you can argue, and I have many times, that this is the best choice for minimizing the effects of finite T noise. And here's another one. You minimize this particular expression. This is the measure of how unsymmetric the waveforms are, and this is that norm, the standard L2 norm on the weights. And this, to minimize this, is just a matter of choosing for the lambda the eigenvector associated with the lowest eigenvalue of M. Is that making sense? And this thing is just choosing the eigenvector for the lambda associated with the lowest eigenvalue. So minimize this, the amount of antisymmetry noise for a constraint on this one of those measures of the total energy in the stack. And that's just a matter of solving this vector equation. Similarly here, we can minimize the amount of acausal energy by fixing the amount of total energy in the stack. And these are normalizing with the other measure of total energy. This corresponds to a generalized eigenvalues. This is very easy to do. It's just a matter of solving that very simple matrix equation. I have now proposed 8 methods by which I would suggest how can we choose the lambdas. And we will see what happens in a little bit. I want to point out, kind of in passing, this is sort of a footnote, the two schemes that use this rather obvious, but it turns out not very good choice for a constraint. They use this L2 norm. Here are the schemes. I want to minimize the anti-symmetry energy for fixed L2 norm on the lambdas. It turns out that the finite T noise actually ends up being proportional to lambda transpose lambda divided by the amount of time you integrate it over. So what that means is that if you're trying to minimize this, what you're minimizing is a ratio of what you might call anti-symmetry noise to finite T noise. And similarly, the causal noise to finite T noise. And so what you're minimizing when you're doing this is a ratio of noise to noise. And it's not necessarily what we really would want. We want some kind of noise to signal. So there's actually a real problem with this. The other techniques, the other schemes are various ratios of noise to signal. And we're going to find out that sometimes they're much better. So I've got 8 prescriptions for these weights lambda. And what I want to explore by numerical simulation is how well they actually work in practice. And I do a numerical simulation on a square array of a scalar wave equation. There's a scalar wave equation. It's got some absorption in it there because it's sigma times psi dot. And it's got our usual del squared for unit wave speed. And it's got various scatterers in here which basically look like little stiffnesses at various positions. I don't know if you can make it out here, but there are large black dots here. Those are where I put my stations. And maybe you can see small gray dots in there also. There are many, many hundreds of them in there. Those are the positions of these little scatterers. And the gray shading, which comes out much better on my screen than on yours, around the perimeter there is the high absorption. And I have noise sources around the perimeter also in rough proportion to the amount of absorption. One of the ways you can get a fully diffuse field, and have no real doubts about it at all, is to have all the sources be exactly proportional to the dissipation. I haven't done quite that. I've also had the source strengths different in different directions away from the center of the array. And this is the first of the numerical simulations. This is sort of a sanity check. I did one fully diffuse 2-month period of correlations between those many stations here, and you find when you do this kind of a stack, a record section and so on, you get a very, very nice result. You can see the main arrival like this. You also see a lot of stuff at late times. That's coda. It belongs. That's actually the Green's function. So what we see here is that in fact I have a fully diffuse incident wave field, even though it was multiple scattering. It's fully diffuse, isotropic, and the stack that I get here looks very nice. And if you look in detail here, you find this is the actual Green's function, which I can also compute, and this is the correlation. You see they line up very, very nicely. There is a blow up. You can see that at short times, all these little wiggles line up very, very nicely indeed. The basic theorem that the Green's function is retrieved from the correlations works very nicely. You also see here a little bit of non-causal stuff. The correlation at short times is not quite 0, but of course the Green's function is 0 at these pre-causal times, and that's because there really was finite T noise. And the red line there nicely describes the amplitude of the noise that's present there, so that means that our a priori estimate of the finite T noise is in fact doing a good job. So that works very, very nicely. That's fully diffuse. The wave field was in fact fully isotropic, and everything worked very well indeed. This is a special case designed to work well with the proposed techniques. I have 2 days, that is I call them days, they're actually 4 weeks long. They have what I call complementary ponderosities. On one day you had a lot of energy coming from, I'll call that the east and so on. And then on another day you had no energy coming from the east, but a small amount of energy coming from every other direction. That doesn't happen in practice, but that's a nice thing for doing the numerical simulation. The nice thing about this choice is that if you took this plus some number, maybe around 10 times the blue one, you'd get something that was constant in angle. So there is a relative weighting which makes things exactly fully diffuse. Neither day is fully isotropic, but there is a linear combination that is. And in fact, because I designed it, the linear combination is something that I know. It's a rather complicated looking table. I think my main point here is that, I don't know what my main point should be here. This is, maybe we should go directly to the next slide and see what comes out of it. There we go. This is the conventional stack where we just took each day as it was and just added them together, and you see, this might even be the one that I showed several slides back, that there's lots of non-causal energy. You're terribly influenced by the large amount of energy that came on the first day entirely from the east. And so that's the scheme number one, the conventional one that works very, very poorly. We can do this flattening where we normalize each day's correlations to the total energy, and it's somewhat of an improvement. In fact, it's a substantial improvement. I should probably mention in passing that flattening is not guaranteed to make things better. It usually does, but it doesn't always. And you can see things are beginning to look better. Clearly, the non-causal stuff that's happening in there is still larger than the red line. What that means is that if you were to integrate for a longer amount of time, you're not going to improve that any. And this is now from scheme number 6. All the other schemes come out about the same. Now, in fact, you get a very, very nice symmetric thing, fairly causal thing. There's some energy here at non-causal time, which there shouldn't be in the actual Green's function, but it's the same level as the finite T noise, so you know that that's not something you're going to fix by playing with the lambdas. You can only fix that by integrating for a longer amount of time. It works really nicely. And again, I should say, the reason perhaps that it works nicely is that it was designed to do so. This is another case. I've got 4 separate days now, each of 2 weeks duration, and these are the ponderosities on each day. A lot of energy on the first day coming from the east, and the other days it's distributed in other directions, but in a not particularly uniform fashion. This set of daily ponderosities has the property that if you added them up in the right way, you could get something that was roughly constant, but not perfectly so. This is sort of what you would expect to happen in practice. There's no linear combination that makes it exactly isotropic. Nevertheless, you could get better than any one of these individual days. I think I won't go through that table. We find that the schemes 3 through 8, the ones where we had a proper denominator, chose weights that correspond to a nearly isotropic ponderosity. This dark line here is the effective ponderosity you would have if you did a conventional stack. And you can see that it's tremendously dominated by the energy coming from the east. If you do one of these other techniques, you find something which is a lot closer to isotropic, but not perfectly so. The schemes are trying to make an effective ponderosity which is flat, but they aren't totally successful at it, and the reason is that there is no linear combination that would make it flat. Nevertheless, they try, and it's rather striking that they do such a good a job as they do, because they do not know the individual daily ponderosities. All they know is the correlation function that they get. They're trying to make it look better by either making the result more symmetric or getting rid of the non-causal energy, and they do this by choosing weights that make this total effective ponderosity much closer to isotropic. There's the straight a conventional stack. Again, it looks quite bad. Here, if you flattened it, you make it look somewhat better, and this is the result from one of the optimization schemes. You find now that the noise in the non-causal region is still larger than the red line, and it should be because the field is not fully isotropic. Nevertheless, you're getting a lot better as you do the optimizing. And this is a rather special case. I think this probably corresponds more to what we'll have in practice, at least at 10-second seismology, is that I have 2 days here, one with a tremendous amount of energy coming from the east, as you can see here, another one with again, 4 days, and another one when there's still a lot of energy coming from the east, but a mild amount of energy coming from other directions. This is my picture of what happens on one month. There might be a lot of energy coming from the North Pacific and a small amount coming from the Gulf of Mexico, and the next day when there's only half as much coming from the North Pacific and maybe the same amount coming from the Gulf of Mexico. I've chosen these such that there actually is a linear combination that makes it isotropic, but it requires a negative weight. So what this would do is say that I'm going to take the correlation from one day and subtract the correlation from another day. It seems rather, it's throwing away a certain amount of information, but it actually makes things more isotropic, so it's better, as we discover. There is the stack for a conventional stack, and you can see it's really rather poor. You see most of the energy coming from one direction like this. This is one of the optimization stacks. It looks much better. It's highly symmetric. This is from scheme number 4, which was minimizing the lack of causality, but with a constraint, which is lambda transpose lambda equals 1. So in fact, it was minimizing a ratio of the non-causal noise to the finite t noise. So what it did, what the scheme in its wisdom did, is it increased the finite t noise, which makes it look horrible. It thought it was doing a good job, but it was not a good optimization. It's not a good criterion to be looking at. So basically I've decided that schemes 3 and 4 with those strange denominators are going to do a bad job, and the reason is that it was it chose fairly large negative weights. It did far more subtraction than it should have. And here we see again, there is the conventional stack. This is the, what is that, scheme 2? Yeah, that's the flattening one. This is one of the better ones. This is from the optimizing of the causal energy to the total energy, and it comes out just about the way you would like. And this one is from scheme 2. It probably made it nice and symmetric or something like that, but it also increased the amount of finite t noise, and that makes it look horrible. So I'm not a believer in the schemes with that funny denominator. Oh, and this is the effective ponderosity that comes from each of those schemes. You can see the simple conventional stack has something which is highly anisotropic, and all of the optimization schemes, including 3 and 4, which had the bad denominator, do a very good job of picking out a ponderosity which is very, very isotropic. They haven't gotten it perfectly so, and they could in principle, but in fact that would increase the amount of finite t noise. So they tend to choose a nice isotropic P, but with very little penalty for high noise. Schemes 3 and 4, which I guess I'm not sure which one's in there, come out to a very nice isotropic P, but the results, as we saw on the previous slide, are really not acceptable at all. So that pretty much finishes what I was going to say. The technique is not too complicated. I think it's fairly easy to implement, and I'm really looking forward to seeing if in actual practice in seismology we can use this scheme for just reweighing the stack before you add it all up in a way calculated to improve measures of how bad the result is. There's a lot of interest in H over V. I'm not really sure how to measure the badness of an H over V. But if you have a waveform like this, then we can say, I want it to be causal, and I also want it to be symmetric. And these seem to be working very well, at least in numerical simulations. I'm very, very much looking forward to seeing if we can do anything with real seismic signals in the way of reweighing the time base. That's all, folks.
Very nice, Richard. I have a question. So about the expense
The question, there will be some questions later on, and the people that are sending questions by streaming, and then people from YouTube platform will help us to answer them. How you say it is not really expensive, but you need to get like a system of equations, a linear scheme of the size of the number of windows, of the size of the number of days for each, or it is
Frequency range
for each.
Some velocities and different frequencies could in principle be different.
I see. So if you have several frequencies of interest, and then you have several windows, you have to repeat the.
So you're having to do matrix manipulations on maybe 100 by 100 or even 1,000 by 1,000 matrices. That's not too expensive these days. Mine were only 4 by 4, so it was instantaneous.
I see.
There is a question of why not break it up into 1,000,000 separate windows. And one problem, of course, is that you don't want to be inverting million by million matrices, right?
No, of course not.
But the other problem is that you end up potentially introducing so much freedom in your choice of lambdas that you can do anything. If you had 1,000,000 choices for the lambdas, you could probably construct any waveform that you like. So there's a limit to how much.
Okay.
What about the physical meaning of lambda? Because I imagine that this is related with Paco's question.
Because you presented lambda as a weight.
A weight
But-
for the signal
Yes,
processing.
in
right.
that sense, but there is a very close relationship with time and distributions. So I detected that it's something for anisotropy or the badness or something like that, but the physical meanings, what do you think,
Physical meanings of the
professors?
lambdas, they correspond to reimagining the original data as if it was louder or less loud on individual days. So it's any given lambda means that you had the same data, but it just had more gain on that day.
So is intensity of the storms is
It's the intensity of the storms,
something like
right?
that.
Right. Except that on any given day, the intensity in the North Pacific and the intensity in the Gulf of Mexico have to get rescaled by the same amount. So it's not exactly, it's the total intensity that day.
Good, thank you. Yes.
Thank you, Paco, for the invitation. Thank you, Professor Weaver. It's very interesting lesson about processing seismic noise data and how clean the empirical, well, in this case, empirical green function. Also, we can see different schemes. How keep the dispersion characteristics if you want to extract surface wave in this case, and also in other cases we can recover body waves or keep the Kodak wave in order to do some straight changes. In this case, we appreciate a very clean empirical green function, but how do you know that all our traditional processing, like 1 bit and whitening the signal, kill surface wave or kill body waves? In this case, we conserve all the green function with body waves, surface waves, and also Kodak waves.
There was a lot there. I don't know that I can get to it all. There is a problem if you're using causality as your measure of badness. You have to know what maximum speed you can tolerate. And if there are going to be significant body waves in the waveform, then that means that you can't set it at the Rayleigh wave arrival time. So that's a problem. And then you mentioned dispersion also. And just as in the standard processings, the way you would study dispersion is to study each frequency band separately and then put them together to find the different speeds at different frequencies. The technique in general is, I guess you were asking, is it compatible with the other signal processing methods? Was that your question? The whitening and things like that?
Yeah, if we need to sorry. In some cases, we apply some normalization, but in experimental data, we see if we apply, for example, 1 bit, eliminate ballistic arrives.
You want to eliminate the ballistic
arrival?
arrival?
In some cases, when we apply normalization, 1 bit or whitening in the cross correlation, some cases it's difficult to recover. For example, if you want to recover surface waves, the dispersion characteristic is lost in some frequency band. Yeah, but in other case, if we want to recover ballistic waves as P waves or S waves, also we can we have to eliminate surface wave. In your scheme, we have a complete empirical green function, okay? But if we try to apply some filter in some frequency band, the complete characteristics of the surface wave, for example, we can recover also some band of frequency where we can do tomography, for example.
Okay. I guess I'd say again that this technique should be applied separately at every frequency, and it would certainly be possible to use a measure of quality that says, let's have a clean Rayleigh wave arrival, or let's look for body waves, or let's not look for the ballistic wave. That should be possible. I haven't considered that you'd want to, but maybe.
We have to try to with subdata. And what happened?
I think the main point is that this reweighing is a free parameter for the signal processing that people have not taken advantage of. And it seems like there are many criteria you could use that you say, this is a good stack, this is a less good stack. Let's choose the weighings in order to get the best, the prettiest empirical Green's functions, by whatever criteria you would like for how pretty they are. All I've done is look at causality and symmetry.
We can apply this methodology. It doesn't matter if there is
I think so, yes. You can imagine that in 1 hour there's traffic on this road, and another hour there's traffic on that road, so you would like to balance them.
Yeah, in urban zone ambient.
Yeah. So I think it should apply in the urban environment at a couple of hertz. It should. I would like to find out. We'd yet to apply it to any real seismic data. And it seems like there's a lot out there. Let's try it.
In Mexico City, we have a lot of. Okay, thanks.
There are other questions. ¿Hay preguntas en el streaming? Según dicen de aquí algunos me dicen que sí, me preguntan. Roberto, ¿esa la puedes hacer?
Sí, es que hace varias, ¿no?
Pero, pues hay preguntas, ¿las tú o las hacemos aquí?
Sí, yo creo que sí, no sé si están las mismas que tiene usted.
Yo no las tengo aquí. Okay. There are several questions by Dr. Matthew Perton, and he asked if each source has a limit frequency bandwidth, should lambda be frequency dependent?
The answer is yes.
The answer is yes. The other question is, the spectral whitening is then more or less the flattening at each frequency?
It depends on exactly how it's implemented. I think the way Benson et al. Implement it, it's somewhat different. My lambdas are the same for every station. You'll notice every station pair has the same lambda. You could ask for the lambdas to vary with station pair. That gives you a lot of freedom, but I tend not to like that because it ruins the amplitudes of the empirical Green's functions. You can't compare them as readily.
I see. The other question Dr. Burton is making, he says, and then the folding the spectrum, is that setting the constant S equal to 0? I mean, folding the spectrum is like flipping.
Oh, folding it over, yes. You could do that. You could do that first and then optimize on causality. I don't like that as much because I'm not really sure what it means physically. It's certainly an obvious thing to do with the signal processing, but I haven't yet decided if that's a good way to proceed with this, is to impose the symmetry and then optimize on causality.
I see.
In a way, to impose the symmetry is to throw away a handle you have on how good the ponderosities are. So I'm a little reluctant. I think maybe you cheat yourself by doing that.
Well, the other question that Dr. Burton is making is how to know anti-causality without knowing the velocities.
You don't. However, what you can do is pick the fastest velocity that you believe in, or you can decide, well, maybe those faster modes aren't that important, or they weren't coming out anyway, so it doesn't hurt to get rid of them. There's lots of other stuff there at the pre-causal time. So it would hurt the waveform a little bit to choose too slow a speed. So yeah, that's the chief problem with the causality thing. If you really expect real physics to be arriving quickly, then it doesn't work as well.
I see. Well, I think this may encourage us to introduce this in the processing, these schemes in the processing of data. Maybe Marcela is thinking about it, and also if there is any other questions, we announce from 12 to 2 because it's just the time we reserve the room, but we don't have to stay all the time here. But if there is another question, Dr. Guzman, please.
Just a couple of simple questions. The first one is, I don't know what T-noise is.
Finite T-noise, that's again, finite T-noise is my phrase. It's the noise that you're left because you've integrated for only 4 months when you did your averaging. It would go to 0 if we had an infinite amount of time to do your averaging over. It's something intrinsic to the process that you can't get rid of except by going to infinite amount of averaging time.
Well, the second question is it's just an intuition, but perhaps you can correct me if I'm wrong. So you have the ponderosity is time dependent, right? And you want to make this isotropic. Mm-hmm. So you are, in a sense, I guess this could be like invoking the ergodic theorem somehow. So if you have if you allow enough time for the evolution of the system, it will eventually reach all the phase, all the points in phase space, right?
Yeah, well,
this will amount to an average in time.
Yeah, but I don't think that our seismic noise is ergodic in that way.
Okay.
Because the storms tend to be dominated by the North Pacific, no matter whether you go this year or 1,000 years from now. Okay. Maybe if you could integrate for 1 billion years, you could get it after the continental, after the plates move around. Maybe it would go ergodic then.
Okay.
That's a cute thought.
Thanks.
So, if there is...
Are you preparing some material about this?
There's a paper, I don't know. I think it's in press. It's been printed now.
I think it's published
in the
already.
Acoustical Society very recently. This is the first time I've presented it, so this is your opportunity to get into it before anybody else can.
We appreciate that you choose to make a premiere in Mexico, the premiere of this presentation, and it's original. It's quite original, and I hope it can be very useful for improving correlations and even the autocorrelations. I'm thinking what would be the right HRV criteria.
I was thinking along those lines. If you have an array and you want H over V at each point in an array, you could choose your lambdas based upon causality but in the cross correlations and use those for your H over V.
Yeah, but so additionally for inversion, people rely also on dispersion curves to improve the quality of the inversion. So at the same, you do the same thing at the same time for the same price, which is okay. So if there is no any other question, I want to thank you all for attending the seminar of Dr. Weaver, the world premiere of this presentation, and we thank him with a big applause. Thank you. No hay más preguntas del streaming, ¿no? Muchas gracias por venir.